Alright, hey everyone. So I realized I should just make videos about different web work questions that students ask about. That will have a reference for the most popular ones. So, alright, let's jump in. Alright, we want to find the mass in kilograms of the following objects. So I'm just going to go ahead and do the cow problem. And, I think that works as an example. So, alright, assuming the cow is a sphere, alright, so we should just call this the sphere problem. The sphere problem. All right, so then that doesn't matter. Oh, it has a diameter of 1.7 meters. Okay, there's 100 centimeters in 1 meter. And that's going to be useful because we have centimeters cubed and here we have meters. And so in the context of the problem, I'm seeing lengths given in different units. I know I wouldn't want to go between the two, but I've also read this a few times. Okay, the density of this sphere is 1.2 times that of water. So the density of the sphere is 1.2 times the density of water, and the density of water is 1 gram per centimeter cubed. Okay, so the density, that's lowercase delta, sorry, of the sphere is 1.2 times 1 gram per centimeter cubed. All right, well, there's no reason to say times 1. We can just get rid of that and say, okay, so here's the density of the sphere. All right, and the radius was 1.7 meters. Okay, well, each meter is 100 centimeters, so really, we're going to just multiply this by 100, this being the radius. It's 170 centimeters. But one way to see that is I need to get rid of meters and make it centimeters. So I need to make it centimeters, and I need to get rid of meters. So what that tells me to do is I should divide the 1 meter over on both sides. And the number 1 is equal to 100 centimeters divided by 1 meter. And since you can multiply 1 by not change anything, that's what we do. We multiply by 100 centimeters per meter. And those meters will cancel, and we're left with 170. Okay. Oh, sorry, I wrote radius. This is the diameter. The radius is that over 2. Okay, so that's 85 centimeters. All right, so now, if I were to find the volume of the sphere, that's 4/3 pi r cubed. So that's 4/3 pi, and then r is 85 centimeters. That's cubed. So, all right, that is what it is. And when I multiply this, the volume of the sphere times the density of the sphere, that's going to give me the mass of the sphere. But the units of that are going to be grams because the density gives me grams per centimeters cubed. So the units for VS, that's centimeters cubed. The units for the density, that's grams per centimeters cubed. So those are going to cancel. We'll be left with grams. Okay, let's do it. So we have 4/3 pi 85 cubed, which I'll just put like this, times 1.2. And now the final units are grams because there was sort of a centimeters cubed here and then over centimeters cubed here, and those are going to cancel, and you're left with grams. Okay, so there's the mass in terms of grams, but the problem says we want the mass in terms of kilograms. So we do a very similar thing to this. We have 1,000 grams and 1 kilogram. So divide by 1,000 grams, and this expression is the same as the number 1, and it has grams on bottom, so I can kilograms when I multiply. So let's actually divide this by 1,000 because I'm really multiplying by this thing here, the 1 kilogram, 1 kg per 1,000 grams, and now the grams go away. Okay, so what's the mass of the cow, aka the sphere? It's this number right here. All right, hopefully it makes sense. Or you can slow down and see. Maybe I should do one more. Let me know. I can always make more videos. But okay, until then, let's move on to the next one that I pulled off. Here, go away, go here, boom. That works. Okay, problem 4. Sweet. Graph of a function contains this point. What that means is if you input -9 into f, the output is 10. Okay? So this function f, the only thing I know about it, is that it'll take the number -9 and it'll output 10. Okay, there's my function f. So then the question says, all right, well, what about the graph of f of x minus 6? What do you know about this graph? And look, I only know one thing about the graph of f, and that is that it takes, well, I shouldn't even say the graph. I only know one thing about the function f. It takes the input -9 and it sends it to 10. So the whole idea is you stare at this long enough and you go, aha, wait a second. What if -9 was equal to x minus 6? That's all. So if x minus 6 was equal to -9, well, let's go ahead and add 6 to both sides. Okay, then x is equal to -3. Okay, well, true or false, when you plug in -3, that's f of -9. So when x is -3, plug it in, you'll get f of -9. Oh, we know what that is. That's 10. So our input was -3, and our output was 10. So what point does this contain? It contains -3, 10. Right, for that graph there, for that function there. Okay, play the same game again here. And the whole idea is the only thing we know about f, the only thing, is that f sends -9 to 10. That's it. So the only x value that I can plug in here and know something is -9 in this case. Here it was -3 because I had to make the total input be -9. Okay, so when I plug in -9 for x, what happens is this becomes a 10. 10 minus 6, that's 4. Okay, so 4. Boom. All right, so last one. Well, the only thing I know about f is when I put in -9. So I guess this has to be -11 in order to make that work. So when x is -11, then I plug in -11, I get f of -9. I know what that is. That's 10. 10 plus 5, that's 15. So that would have to be on that graph. Okay, that's the whole idea. This is getting at shifting and stuff, but that's what the activity is on Wednesday. So we'll talk more about that then. All right, on to the next one. Okay, this is just a quick review on what the heck is ln of x. Let's go ahead and go a little wider. Ln of x. So if it equals some number, like say 3, okay, then if we had to solve for x, it's actually like much easier. Or well, let me just what is the statement saying? It's saying e to the 3 is equal to x. These are saying the same thing. In general, ln of x equals y is saying e to the y is equal to x. So, if we had ln of e squared is equal to something, okay, you always just want to rewrite it. So what's the pattern? Well, this output is the exponent, okay? So this is saying e to the something, okay, there it is equal to, and the input is x, so we have e squared. And now in this expression, don't overthink it. This tells you something is equal to 2. Oh, so we figured it out. This number here should have been 2. And in general, the natural log of e to the x is x. Okay. If we rewrite this, it's just going to say e to the x equals e to the x. Because what do? We take the input and we put that on the right-hand side. Input, right-hand side. And we take the output and we make that the exponent. Output, exponent. So, okay, quick and dirty review. Let's also, if you had to write 2 cubed, well, you could write this as the square root of 4 cubed. I don't know why you would, but you could. Okay. Very similarly, look at this. If x was equal to 2, so let's introduce another thing. E to the natural log of x is equal to x. Oof. Okay, let's run through this real quick. Sorry, I'm going to pause that talk. All right. So let's see. This scenario, we're starting out with something that looks like that. Okay. So what's playing the role of y is natural log x. Okay, so what's this saying? This is saying, let's start to color code. What's playing the role of y is natural log x. And let's see, so y, here's y. Here's this. I'm trying to keep it, whatever that purpley pinky is the exponent on e. And it's also this, side here. Okay, and that equals natural log x, and I took this x and put it in there, right? So these are called identities. No, wait, what am I thinking of? Sorry, these are inverse functions. Sorry, it's late. It's almost 11. Okay, this fact. Let's use it right here. So I'm going to take the number 2, x equals 2, and I'm going to write it as e to the ln of 2. So 2 is e to the ln of 2. That's the whole point of what this is saying here. If I sort of put a 2 in for x, put a 2 in for x, 2 is equal to e to the ln of 2. So, okay, this is what seems like a silly thing. Why would you ever want to do this in your life? Well, in general, if you have 2 to the x, then you can write this as e to the ln of 2 to the x. Okay? And I still answered, why would you ever want to do this? Well, it's because now you can just, any base you have, okay, b to the x is equal to e to the ln of b to the x. And then we should use rules of exponents. And one way to think of this, well, we talked about this a bit in class, but so power to power, you multiply powers, but one way to think of it as to why this x is right here is because we sort of have e to the ln of 2 times e to the ln of 2 times e to the ln of 2, and on and on and on, e to the ln of 2. And how many copies do we have? Well, we have x many copies, right? Because that's the power on e to the ln of 2. Okay, so when you have x many things, right? So if I have 2, 2, 2, and I have it 3 times, that's the same as 3 times 2. If I have it x times, that's the same as x times 2. So that's what's going on here. Anyway, all right. That was a quick and dirty rules of exponents. Okay. So why does this matter? Now we can just always talk about natural log and base e and forget about any other base. So if we go up here, hey, look, we want to change the form of something into this. And the whole idea is to say, well, e to the x ln r, that's just a silly way of writing r to the x. And so you stare at this long enough and you realize, okay, r is 2. So I'm actually going to have 2 to the x is the same as e to the x ln r. Nope, ln 2. Okay. And, so r was 2. All right, and what is this a here? It's just whatever's out front there. It's 4. All right. Okay, so there's some quick stuff there. Most of this web work was playing around with rules of exponents and stuff. And for the most part, I think you should just play with it and figure it out. You might kind of hate me for that, but I guarantee you've seen rules of exponents before. And if they didn't, people lecturing you on them on the past didn't change much, then just trust me, just do it. We'll spend more time on it if we need to in the future. Okay, so let's talk about half-life. This is something that sometimes we should really go over. So let's see. Carbon-14, T years after the death of an organism is given by this function. Okay. And then you might be thinking, what the heck is Q0? What is that? It's just some fixed number. And if you plug in T equals 0 into this function, there's my T, it kills this whole exponent. So I have Q0 times e to the 0, but anything to the 0 is 1. So I just get Q0. So in fact, Q0 is just a cutesy way to talk about Q at time 0. And it's called your initial condition. It's just how much there initially was. And it turns out you don't need to know it. So let's read the problem. When will 1/10 of the original carbon-14 be left? So the original carbon-14, that's how much you have at time 0. And we have a name for that. It's Q0. So Q0 is how much you have at time 0. And I'm only going to have 1/10 of it left. So 0.1 Q0. That's how much I have left. And I need to model it with this equation here. Oops, sorry. So that's equal to Q0 e to the, and then in my case, negative 0.12314 t. All right? And notice you can cancel these Q0s. That's why it didn't matter. Didn't have to tell you what it was. So now we have 1/10 is equal to e to the negative 0.12314 t. So take the natural log of both sides. And hey, we just talked about this, and I probably just erased it. Sure did. It's almost like I should pay attention to the future. Okay, so the reason we do this is because the natural log and the e cancel. They're inverse functions. And what's left over is negative 0.12314 t. So natural log of 0.1 is equal to this. We want to solve for t. Well, that's natural log of 0.1 divided by negative 0.1230124, and there it is. Okay? So this gross expression goes right there. All right, if this many grams are present after this many years, how much was originally present in the organism? Okay, so let's see. We have 0.043. Let's clean this up a bit. 0.043 is equal to Q0 e to the negative 0.123124 times 9,000 times 9123. Okay, all this is up in the exponent. Oh, look, this is a number. Your calculator will tell you what it is. This is a number. Let's just divide that number over there, and you get Q0, and that's what goes right there. Okay? Cool. So, that's that one. One more to go. One more to go. Sweet. Less sweet. Less sweet. All right, whatever that will do. All right. Consider that function. All right, I considered a function. If s of t is, is it increasing or decreasing? You should be able to answer this without looking at a graph. I agree. So, look, e to the 2.75 to the t, that's the same as this. Ignore the number 5 for a moment. That doesn't change whether it's increasing or decreasing. That's just the number 5. But this part is the part that's changing and moving. So, okay. This number here, it's a pretty big number, but all that really matters is that it's bigger than 1. Okay, think of a number bigger than 1. I'll use 1.001. If you start to raise this to bigger and bigger powers, so like 2, and then 4, and then 8, and so on, it's going to blow up. It's going to head to infinity, okay? Whereas, if you take a number that's less than 1, like 0.9, I'll just do a half, because everyone's coming from half. If you raise it to bigger and bigger powers, the 1 up top stays the same, 2 cubed, this is 1/8. And in fact, if I raise it to the, let's say 30th power, this is 1 over 2 to the 30. That's very, very tiny, okay? Depending on your calculator, it might not get there. Okay, so what's going to happen is it's going to increase. Yeah, because this thing's growing because the base is bigger than 1. All right, so great. If this option menus, okay, whatever. If the function is increasing, well, it is. Find the doubling time. All right, and then we should probably also talk about half-life, so I'll talk about both of those. Doubling time. So here's the thing. When time equals 0, so the initial time, you plug that in. That kills the whole exponent, and e to the 0 is 1. So all I'm really saying is s of 0 is 5. Okay. Now we want the doubling time. Now, I didn't need that, but whatever. So 5 doubled is 10. 10 is going to equal 5 e to the 2.75 t. All right, now the reason I did not need the 5 is because what always sort of happens is this number out front, the initial condition, doesn't matter. What matters for doubling time is the other stuff is going to equal 2, okay? E to the 2.75t. By other stuff, I mean the exponential growth part, okay? That needs to equal 2 because that's how you're going to turn this 5 into a 10. So then you solve for t by taking the natural log of both sides. Natural log of 2 is equal to, and when I take the natural log on the right-hand side, it's the inverse function, so it undoes the e, and then you can solve for t. Okay, I'll let you do that. Now, if instead you had to do a half-life, then you would just do something like 1/2 is equal to e to the 2.75 t. And you could actually solve this. It turns out that t is going to be negative, whatever that is. But you can't really have negative time. So the reason why they talk about increasing or decreasing is because what these look like. So here is something like e to the t, whereas here is something like 0.1 to the t. Okay, nothing special about e except that it's bigger than 1. Okay, so starting at time 0, e to the 0 is 1, 0.1 to the 0 is 1. So they start at the same place. It's just here I'm going up and here I'm going down. So it's easier to hit a half at some positive time value. Here it's easier to hit 2 at some positive time value. But since we can't rewind time, I can't hit a half back in time. Okay, anyway. So that's how you do that. For what value of t does this happen? Well, set it and figure it out. What do I mean? What do I mean? Take this number and plug it in. 299,370.709. Yep, that's it. That's a question mark there. Okay, this needs to equal that because this thing was s of t. Then you take natural log, solve for t. All right, see you next time.